Now that we've seen how to find a impulse response from and transfer function from a um, differential equation, we'd like to be able to say infer what the impulse response is by just looking at a single input-output pair. So that is, if I give you a system like a black box and you put in an input signal and you measure the output signal, then can you try and determine what the transfer function is for the box? And that's really important because sometimes the box is like some natural system that you don't have any control over, or it could be some component that you've bought or something else. In essence, a system that you do not get to design yourself. So the learning objectives for here are to be able to find the impulse response of a CT system using just an input-output formula, or rather an input-output relation, a single input-output pair. Then you want to be able to explain, again, this reason that I sort of gave just now about why you want to be able to do this, which essentially has to do with this problem called system identification. How do you identify what the transfer function is of a system given some input-output measurements? So suppose I give you an LTI system, and it has an impulse response h of t, but you don't know what h of t is, right? So we have some x of t that comes in, and then y of t comes out, and you measure a particular x of t, right? So you take this particular x of t here, which is e to the minus 3t u of t. So what does that look like? It looks kind of like this. And then what you get out is y of t, which is summation of a scaled version of the input signal plus this other output signal, e to the minus 2t u of t. And so one thing you might think about right now is that, well, you've seen a lot of examples of a single pole system signal entering a single pole system, and you get out this combination of the two of them. So you might suspect that h of t has a single pole, right? Because we've seen a lot of examples of this where you essentially in the time domain you're convolving two decaying exponentials, and you get out this sum of these two decaying exponentials. So we kind of suspect that maybe it's something over s plus 2, for example. That's kind of what we would guess. But let's try and find it, using math. So to find this h of t, we first find the x of s and the y of s, and then we find h of s, right? So, and then we can just invert the Laplace transform. So let's take the transforms on both sides. So this, remember, is e to the minus 3t u of t. And so this corresponds to this, and the ROC has to be over here because this is right-sided. Right, so we have a right-sided signal, so that the ROC goes from the pole minus 3 off to if this is minus 3, it goes in the right half plane. And for y of s, well, we have this minus 1 over s plus 3, and then we have this, so this corresponded to minus e to the minus 3t u of t, and this s plus 2 corresponds to e to the 2t u of t, minus 2t u of t. Right, so this was our y of t, and you do this out and you multiply, cross-multiply, and gather, merge these two fractions, and you get a simple 1 over s plus 2 times 1 over s plus 3 expression for the output Laplace transform. And here, the ROC has to be the smaller of the two ROCs, so there's a pole at minus 3 and a pole at minus 2, right? So here's a pole at minus 3 and here's a pole at minus 2, and we have to remember the ROC can't contain any poles, so we're going to choose the ROC that goes from minus 2 to infinity. Right, and that we know it's right-sided because the signal y of t is right-sided. So then we just divide the two, and we get exactly what we kind of expected, something over s plus 2. In fact, something even the simplest thing we can get, 1 over s plus 2. Right, which means that h of t, just doing the inverse Laplace transform, should be e to the minus 2t u of t. And just to be extra safe, we have to make sure we want to look at the ROC of this h of s. And so we need to make sure that the ROC is consistent with having this ROC for Rx and this ROC for Ry. So we need to make sure, ensure consistency. And what do I mean by that? Well, if I intersect RH with Rx, I'll get Ry. That's what I mean by consistency. So note what we've been able to do is given just a single input-output pair, here's a single x and a single y, we're able to compute h of t, the impulse response of the system, just from that input-output pair. We didn't have to have a differential equation. We didn't have to have an explicit description of the system. This is just using essentially black box access to the system. So what's the step-by-step process here? Well, the step one is to, you want to find the Laplace transforms and make sure you also find, we need the ROCs. We need to find these ROCs because remember Laplace transforms are only defined if you define also the ROC for the Laplace transform. Okay, then we can calculate the transfer function. So we get the transfer function. And then we need this appropriate, what we were calling consistent ROC, RH, so that RH intersect Rx is equal to Ry. So then we're going to, and then the final step is of course to use partial fraction expansion or long division or just straight up taking the inverse transform to get your final h of t. Right? And so that's the three-step process. You take Laplace transforms, divide, take the inverse Laplace transform, and whatever work you need to do to get the inverse Laplace transform. So just to reemphasize the point I brought up at the very beginning, this is a really important process because if you have an unknown system, that is you're given black box access to a system, you can design a probe X, measure Y, and then try to estimate the impulse response or the transfer function. And this process is known as system identification. And this is like a major topic when we talk about systems theory. If you take a follow-on class to this, especially in problems of control, where you often have like some sort of mechanical system or electromechanical system or some physical system that you can just try inputs and outputs to try and figure out what its input-output relation is, and you kind of hope that it's an LTI system or that you can model it as an LTI system. Okay, so let's look at another example. So here we have x of t is equal to e to the minus tu of t, right? And so this is going to give us x of s is 1 over s plus 1, and the ROC is a right-sided ROC. So this is again right-sided. Right? And then we have y of t is now more complicated. It's got three terms. Scary. Right? But we have an e to the minus tu of t. That corresponds to this one here, and then we have two more terms, e to the minus 3t term and an e to the minus 4t term. So we can just, this is all of these things are right-sided causal looking things. So we can just write down the Laplace transform. We get a sixth over s plus 1 plus a half over s plus 3, and then minus 2/3 over s plus 4. And if you do the algebra, or if you want, you can do it in MATLAB. You can get this final transfer function, right? And so it's again, I worked out the numbers so that it would be nice and simple. It's just 1, 0 at minus 2 and poles at minus 1, minus 3, and minus 4, right? And that's the output signal. And so again, we need this ROC to be have no poles in it. So we're going to choose the rightmost pole, which is at minus 1, and we're going to say the ROC contains everything to the right of this pole. Note that we have a 0 at 2, but it doesn't matter because that's a 0, and ROC can contain zeros. So now we get to step 2. Step 2 is just dividing to y of s by x of s to get the transfer function. So here we're dividing these two terms here, and we get a much simpler transfer function with two poles. So notice y of 3 had 3 poles, x had 1 pole, so you think h should have 2 poles. All right, we can do partial fraction expansion on here, so we do partial fraction expansion. And maybe you want to pause and do that for yourself, but we get this kind of simple formula here. Again, because I tried to make the numbers work out correctly. And here we have to look at the ROC. Again, the ROC for RH, in order to be consistent, is going to have to be real part of s is greater than minus 3, and that's to make sure that we match the ROC for the output y. Because remember, there's no pole at 1. The pole at 1 comes from the input x. So this ROH is consistent with the original ROCs. Okay, so we just then take the inverse Laplace transforms. We get minus e to the minus 3t u of t from this first term, and then 2e to the minus 4t u of t from this second term. Okay, so let's do another example. This one is for a non-causal system. So suppose we have the following input-output pair. We take the same, we take a similar looking thing as we've seen before, right? We get e to the minus 3t u of t for x. So that's s 1 over s plus 3, with the ROC being s greater than minus 3. And now for y, we have minus a half e to the minus t u of minus t. So remember, this is, now look, this is left-sided. And then minus a half e to the minus 3t u of t. So this term and this term are going to correspond to each other, but this left-sided term is different than what we've seen before. And that's what I mean by talking about a non-causal system. So now remember, for y of s, then this first left-sided term just turns into a 1/2 over s plus 1, but now the ROC for this one is the real part of s is going to be less than minus 1. But then for this one, the ROC is a real part of s greater than minus 3 because it's a right-sided signal. So from this term, we're going to get this second term here, and when you take the Laplace transform. We can do the algebra to cancel them. We get something nice looking because, again, I made this up to make it look nice. And then we take the ROCs. For Ry is going to be like the intersection of the sum of these two terms, right? So we get this two-sided ROC between minus 3 and minus 1. There's two poles here. Right, so this is a two-sided y of s. Okay, so we're going to divide now to get the transfer function. That was step 2 in our little formula. The s plus 3 is going to cancel. And so we're going to get 1 over s plus 1. But now we need to make sure this is to be consistent. To be consistent, the ROC has to be a left half plane. Left half plane, right? So we're going to take the other type of inverse for this Laplace transform, and we're going to get h of t is minus e to the minus t u of minus t. Right, and this is because we need, remember, Rx intersect Rh to equal Ry in this case, because we have no pole zero cancellation. The main challenge, of course, is to make sure that these regions of convergence are consistent, as I said before. So basically, and I did this in the previous example, so I'm just reiterating here, you want to make sure that your Ry is your region of convergence for the output signal is the intersection of the input and the impulse response. And of course, this is assuming no pole zero cancellation in the process. So you have to first check to make sure there's no pole zero cancellation. But in our examples, we could see this. So in the first example, we had actually this condition that we just needed RH to be bigger than Rx because the output Y had a region of convergence that was essentially equal to Rx. So RH can just be anything that's equal to Rx or bigger. And in the other case, we had a two-sided region of convergence and one-sided for the input. The output was two-sided, so we know that the input had to at least be left-sided, and so we can get this constraint here out of the impulse response H. So again, drawing the pictures as I was doing earlier could help quite a bit here, and I think that should make it easier to see how you can pick an RH such that Rx intersect Rh is equal to Ry. So as a try it yourself, here I'm going to ask you to start with an x and h, convolve them to get y, and then try and start with x and that y to see if you can get back the original h. Right? So given x and h, compute y. You can do that using Laplace transforms, and then start with this x and this y, and then recompute h, right, from x and y. And you can check then, because you know what h of t generated the y, you can make sure that the h that you determine rather is the correct h, the one that you actually use to compute y. So I hope that makes sense. And again, the whole name of this game is to be able to identify systems and figure out what the transfer function, what the impulse response is, just by probing it with an input and output. And so this is one way you can think of this as a type of a learning problem, where you're trying to learn the dynamical system, or learn the LTI system rather, in terms of by looking at its input-output behavior.